And this is skipping a lot of really big points, but it's mostly true. Again, when I want to prove something that is dynamically false, I suppose it's true. I want to show there's no really strong logic, so I suppose there is one, and then I watch the world explode, right? It's a fun way to do things. This is my symbol for first order logic. I'm not really sure why that one's used. There are much better symbols to use, but that one's the one that's used in literature, so I will use it. That is a subscript 1 rather than an I. Again, I have no idea why mathematicians can't simply use numbers. We seem to have a thing against that.
We don't like them.
Yeah. I think the linguists invented them. We can blame that, right? Yeah. Yeah. What?
Carry on.
Okay.
They have some.
Yep, I go around them.
Okay, that's
Alright,
Guys.
so this is shorthand for L is a logical system. It is strictly stronger than first order logic, and it has nice properties, right? In particular, low times scoring compactness. A logical system is just a way of writing sentences. It's a collection of things that are true in some structures. If you want to think about it this way, you can think about it as a collection of sets of structures, right? Over here is my universe of all possible structures. That's very big, in fact. Here's the structures in which some sentences are true. Here's the structures in which some other set of sentences is true, so forth. Each sentence is a way of cutting up this universe into little pieces. If you want to think about it that way, you can. It's actually a very good way to think about it. And then a general sentence is just some way of cutting this into a piece. And then I can define logical system. A general sentence is a collection of structures, closed under isomorphism, and rename the property. So, what do I do? I take two structures that are basically the same. This symbol means that all first-order sentences true in this one are true in this one. As far as first-order logic can tell, they're the same universe. If you want to think about it this way, and actually this is kind of fun, the first-order logic sentences describe phenomena. These two universes are the same up to noumena. I'm basically saying this to make Peter's head explode. It's not working. He's smiling evilly at me. I'll shut up now. Basically, I can't tell the difference between these two structures just with first-order logic. That doesn't mean they're the same. Remember what I said about first-order logic being weak? There are structures that are radically different that first-order logic can't tell apart. In fact, I want these to be two of those. Because I also want to assume they are not the same in terms of L. First-order logic can't tell them apart. This magical logical system that we just created can. Right? That's an example of it being more powerful. Here's the fun part. Having got a sequence of symbols that means absolutely nothing, that's completely unintelligible, I draw a smiley face. I built myself a new universe.
Oh, that's why.
Yep.
Yep.
Here's M, right? I put this structure inside. Here's N. This one winds up inside as well. And for the third part, this is very weird, but it'll almost make sense shortly. This is what is called a finite isomorphism. There's a theorem which I'm not even going to try to prove, called Versay's theorem, which sucks balls, the proof. But the theorem is actually pretty cool. And it says whenever two structures are the same as far as first-order logic can tell, they look the same actually on finite bits. So what that means is, I'll erase my picture of a universe of universes.
Now, is that an if and only if statement? Or is that...
If and only if, actually, but I only use one direction. Here are two structures that first-order logic cannot tell apart. Take a finite piece of this one. It's got to be the same as some finite piece of this one. The intuitive reason is, if this finite piece doesn't look like any finite piece of this, then I can say, using first-order logic, this piece lives somewhere in my universe. That will be true here, but not here. So they have to look the same on finite levels. First order logic can do finite things really well. So basically a finite isomorphism. Every finite piece here, I send to some finite piece here. Every finite piece here, it's a finite piece here. And backwards, right? Every finite piece here has to look like some finite piece here. So that basically gives me this massive two-way correspondence. These might not be the same structure, but they look the same at any very small level. And the connecting the small-scale pieces to each other is a finite isomorphism.
How on earth would you visualize something?
I did Z and Z plus Z are like the ones that made the most sense. I was trying to
Yeah,
think
why
about
should
it,
we
Is
like,
that actually a back and forth
exactly.
argument, or is that?
Yes,
Okay.
it's,
You know, like
I'll do that one.
he's gonna sorry. I was considered
And it fails.
the integers and the integers plus the integers, like anywhere
Oh,
in
I
the
see.
integers,
They're
you'd
not
be
the
able to
same.
find
They're
something.
not the same structure, but you can look at Z and it will be the same as Z, and then you can look at the other Z
Yeah.
and it will be the same as Z.
And no thunder has been stolen.
Yeah, dude,
Sorry.
way to steal my thunder. Here's an example of what they were talking about.
Sorry.
Over here, I have the integers, right? Very well understood structure. I'm looking at it not as algebra. I have no plus or times. I just have less than, or greater, whatever. So I'm looking at it as a linear order. Has some nice properties. It goes off to infinity in both directions. There's no first or last element, and it's not dense, right? There are elements in between which there is no third. Like between 2 and 3, there is no third integer. Over here, I have the much weirder, so this right is Z. Over here I have what I'll just call Z plus Z, which is I take a copy of the integers, and I glue onto it another copy. This goes to infinity in both directions, has no endpoints. It almost looks the same as the integers, right?
Correct sum or?
With linear orderings there's no difference, but yeah, sure.
Okay.
The only part where this doesn't look like the integers is here, right? Where I can go to infinity inwards. I can't do that in the integers, right? If I take any two integers and start counting towards each other, I'll meet in the middle somewhere. Here, I can keep going to infinity towards each other and they'll never meet. This is not the same. But any finite piece of this just looks like a finite chunk of natural numbers, right? So I can't distinguish between these two things in first order logic.
Wait, how can we distinguish between those humans?
Interesting. That would suggest that humans don't live in first order logic, wouldn't it?
It would. That hurts a lot.
Or that would suggest that somehow we're not actually distinguishing between them. Tell me, if I gave you two infinite sets of numbers, could you distinguish between them?
You'd have to give them to me, and I'd have to try.
Like you can distinguish between the description.
Like I could find that there were two copies. I could, if I could really move infinitely fast over
That's
them,
the problem.
I could figure out, oh, there are two copies of these weirdo things.
That's the
Like-
problem.
Mm.
Right? Here, I gave these two in a nice way. I drew one of the copies, and then I drew the other. What if I gave them to you like this? There's a point over here, and 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 just kept going to infinity. You'd have no way of telling whether I was counting integers or these crazy things. Because at any step of the way, I only would have given you finitely much stuff. So actually, we can't tell the difference between these two things. We can just tell that there should be a difference between them, if we actually know what we're talking about. Don't think too hard about it, you'll wind up behind a refrigerator with chicken.
I'm close.
So,
Can go for it.
Just
I have my finite isomorphism.
We'll buy you one.
It takes finite pieces of this universe and puts them over here. Or it takes finite pieces of this universe and puts them over here. That's why it's a sort of double arrow going from them. The little lines of teeth, besides looking kind of cool, are a technical thing having to do with exactly how I describe finite isomorphisms. But basically, this is a very big math, like mine. Nobody laughed, so I better wind this up quickly. So, I do two things. First, I make everything small. With Lowenheim's golem, all of this, even though there's a huge structure, this has two sub-universes in it, right? All of this is countable. This just makes things easier. Now, here's the cool part. I have countable things which look the same on all finite bits, right?